Good morning, everyone. In the today's class of this operational research, the extension to this replacement theory, as per the previous class, will be continuing. So, replacement, we already have a clear cut look that upon the time basis, economical constraint, and priority of work, and the conditions related towards the working environment leads to the deterioration of the particular materials that leads to change the particular components which has got failed in the equipment completely and leads to the effect for all the system, and hence the replacement commence over a good conditions over there. Even regarding the maintenance cost of an equipment also increasing with respect to the time, that is another factor, and thus it is becoming more economical towards the replacement of this particular old component or equipment with respect to a new one. So we have been seen different criteria that huge investment cost of replacement other than the 1 year, and second criteria that is incrementing of the maintenance cost after crossing a particular time expectancy, and considering with respect to the time bound and economical bound, and depending upon the operating parameters and the conditions of working, we came to a simple formula that there is a need to formulate a most economical replacement policy. So, what is the optimum conditions that are need to be entabulated for the replacement policy, which is in the best interest of the system. So, that need to be analyzed. So, coming to that particular point, in how many ways or different types of replacement problems are existing under these conditions, we'll be having a detailed look. First one, replacement of a major or a capital item that deteriorates with respect to the time. So, upon the time factor is considered, there is nothing but machines, trucks, expectancy of time. Replacement of an item in anticipation of complete failure, the probability of which increase with respect to time or age. So here it leads to the expectancy of the lifetime period. So complete replacement is necessary over here. And the problems in morality and the staffing. So in some conditions, without any proper operational mode, or if not the particular person, not a skillful persons existing over there, simultaneously the instructions within the steps or sequence of operation will leads to the deterioration of that particular material. Hence, replacement of that particular equipment is hence necessary because of its outdating structure, and as per the new research generations, new developments, or the features that has been incorporated in the existing technology to the advanced technology. Most probably, this replacement of major or capital item deteriorates with respect to the time, as you have been discussed that related towards the machineries and replacement of the trucks when the uh, advanced conditions investment has been increased and maintenance cost has been very much increased drastically after crossing a particular time period. Considering, for example, for a machine, The maintenance cost always increases with respect to the time and stage comes. When the maintenance cost becomes so large that it is economical to replace the machine with a new one. I think but almost as we have discussed in the previous class that if the 50% of the maintenance cost is equivalent to the investment or the capital cost of the particular item, almost it increases with an additional cost with respect to the time basis, then it leads to an increment and compulsory replacement of that particular machine with a new one for the commencement of task that has been assigned. And hence, a problem of replacement in that case is to be found out as per the best time, I think, but at which the old machine should be replaced with respect to the new one. So, how to find out that replacement? In what parameters we have been discussed that timely basis and maintenance conditions and the capital cost containing. I think but scrap value is constant, considering the scrap value is constant because if it at all not it be useful for the utilization, then the money value is not considered, and hence a formulation has been traced out for finding the best replacement with respect to the time basis that the total cost of the machinery in n number of years. So here n specifies to n life expectancy of the particular component or machine when it is being assembled is equal to cost of the machine, that is capital cost of the machine minus scrap value of the machine plus total maintenance cost in the n years. So here n refers to the lifetime. So nothing but after purchasing that n number of years. If for example n is equal to 4 or 5, and we'll be substituting the similar value in the case of this maintenance cost. Here C refers to the cost of the machine. S refers to the scrap value of the machine at that time. That is nothing but with respect to the T, maybe of within time related to the years or days or operational sectors, and cm of t, that is maintenance cost of a particular machine at a time of t. So it increases with respect to the time. And coming to the first case, here there are different conditions as you have discussed with respect to the time basis, with respect to the economical basis, etc. So first considering the case one, when t is continuously variable, when t is continuously variable. So here t refers to that the time constraint. So here the best replacement has been assigned to that of with respect to the time of the machine, lifetime of the machine. So if the time t is continuously variable upon the operational sector, and hence the total maintenance cost of machine in n number of years is that the total cost of machine is equal to cost of the machine minus scrap value of the machine plus the total maintenance cost in the n years. So n may be of 2 years or 3 years, that will be depending upon the type of material or machinery that is being utilized. It is integration of 0 to n c minus s plus integration of 0 to n of cm of t, that is cm here refers to the cm of t refers to the maintenance cost, s refers to the scrap value, nothing but the value of the scrap which has been removed material. C is the cost of the machinery. Hence, the average cost of maintenance per year if you have been considered, the average cost of maintenance per year during n years is given by. So you are calculating with respect to the n number of years, n years. That is an is equal to the cost of the machinery minus the scrap value plus integration of 0 to n number of years with respect to the maintenance required with respect to the time bound in n number of years with that changes with respect to the time. So always the maintenance will be changing with respect to the time, as you have been discussed that the criteria of replacement sector is being taking place with respect to the time bound. Hence, upon this simplification, upon simplification, we are being getting that an is equal to, that is average cost of maintenance is equal to, for n number of machineries is equal to the cost minus scrap by n plus 1 by n of 0 to n of this maintenance cost with respect to the time that varies. So considering it is an equation number 1, and now we'll be calculating at a minimum range and at a maximum range. There are two different conditions need to be characterized with respect to the base constraint. Minimum range, one it is minimum range and next one it is a maximum range. So minimizing relates to the differentiation and maximization relates to the integrational factors. And on a combination, the signature or sign verifications also plays a major role, that applying the differentiation function for the an, that is d by dn of an is equal to minus of c minus s, that is investment cost of the machinery minus scrap by n square minus 1 by n square of integration 0 to n of this maintenance cost of t dt plus 1 by n of c minus t. So upon simplification, now we'll be getting this value from the equation number 1 upon differentiation for the from the minimization characteristics. Hence, the maintenance cost of that particular machinery at a time t is equal to the average cost of the machinery per year. So average cost. So average here in the sense overall maintenance cost of the machine when considering with respect to the time basis at a level of t is equating with respect to the average cost of the machinery per year. Hence, upon the time basis, the average cost of the machine per year is minimized by replacing it when the average cost of date becomes equal to the current maintenance cost. So it is before itself minimum cost of the machinery at the time t, that is equating with respect to the average cost of the machine per year, and upon this we are having the d square of a of n minus dn square, that is differentiating derivating with respect to double derivative. By having that average cost of the machine per year, it is minimizing per replacement upon the average cost to the particular date, that which becomes equal to the current maintenance cost. And when it reaches to the current maintenance cost, there is a major point with respect to the base average cost, then it is simultaneously doesn't supports for the maintenance also as well, and hence complete replacement is necessary. For the maintenance, the replacement is not at all sufficient. Only for the components replacement and acting with respect to the common machinery. And hence the entire equipment or entire machinery need to be replaced, because instead of spending a much amount, that is 50 to 60 percentage greater than that particular amount, and that is equivalent with respect to the investment cost that creates the current maintenance cost. Hence, it is unfeasible for generating the particular machine to be replaced. Moving on to the condition number two, second case, when the time is an discrete variable, nothing but it takes in values of, for example, it may be of 1, 2, 3, and so on, extending for n number of years. At that particular time, the total maintenance cost of the machine in n number of years is sigma of maintenance cost of machinery 1 to n. M of n is equal to m is equal to 1 to n with respect to the time, and hence it is a discrete variable that it maybe if got failure in 1 year, maybe of getting failure in 2 years or 3 years, you can't say it. And when n is equal to, we'll be considering for how many number of years that the machinery need to be replaced. Hence, therefore, in the case of this average cost of the machine per year during n years in a given time, so it is calculated by C minus S plus sigma of m is equal to 1 to n of this maintenance cost of t by n is equal to total cost minus the scrap cost by n plus 1 by n of sigma of m is equal to 1 to n maintenance cost of t. That is the equation number 2. And we are having the condition that the average cost for n number of machineries or n number of times is minimum for that value for n for which it will be getting varied continuously, where delta a n minus 1 less than 0 less than of delta a of n. So here average maintenance for n number of years when the t is considered in the case of years is less than the n minus 1 condition is less than or equal to 0, or that leads to less than of delta average cost for n number of years, n number of time factors with respect to this machine, leads to the following formulation, that is delta of a n is equal to a n plus 1 minus a n. So total a n plus 1 minus a n, that is c minus cs. We are also having a of n plus 1 formula, and here we are having the a formula, a n formula, and a n plus 1 formula. And here, upon substituting, subtracting of both the equations, upon substituting in this particular delta a n, will be having a following relations. And we are having a minimum constraints from the characterization of this equation number 2, which have been considered as equation number 2. An is minimum for value of n for which the conditions here specifies that delta an is greater than 0 and delta an minus 1 is less than 0. It is also clearly specifying that here it is an minus 1 less than 0 less than delta an, and hence this an delta a of n is definitely greater than the 0. That's what here it's clearly specifying. Simultaneously n minus 1 leads towards the less than 0. So this is the condition that we are having specified. So upon substituting that equations here, the simplification, upon simplification we will be obtaining the equations as follows, that minus of a n by n plus 1 plus of 1 by n plus 1 of c n plus 1 of t is greater than 0 as a n factor, a n minus 1 factor, n plus 1 factors which have been considered, the cost of c n plus 1 of t, that is greater than a n, and obviously c n of t is less than a of n minus 1, and hence Upon simplification, as we have got the equation that is related to the equation. Finally, by the obtained relations, that is average cost and the total cost maintained with respect to the variations with respect to the time basis, we can conclude by following factors regarding the replacement of machineries. So only the machinery need to be replaced, or maintenance need to be performed to a particular extent of time period, and later on after completing that maintenance we need to be replace a particular problem, particular component replacement, that will be verifying. So that will be based upon the following criteria, that is, do not replace if the next year's maintenance cost is less than the previous year's average cost. That's the most point. Already in the questions in the previous class we have been discussed with respect to the example format also, that the cost of maintenance is crossing than the last year and increasing suddenly from the first year to the second year at a range of 10 times than the first year in maintenance cost. So in such a cases, immediate replacement is required, but there is a valid point that it should not be replaced when the maintenance cost is very much less when compared to the previous years. Hence, the replacement, if the next year's maintenance cost is greater than the previous year's average total cost, then it is suggested to maintain or for the replacement criteria. We'll be having a small instance. A machine is continued up to the time the average cost per year, including all the costs, that is new machinery, maintenance cost, including of the total cost, etc. of that particular machine decreases and is replaced at the time when its cost begins to increase. So it's clearly specifying the justification of the above both the points, that is, do not replacementing of the machinery or the component when the total average cost is very much less than the previous year's one, and replacementing, that is next generation, if it is average total average cost is greater with respect to the total cost. So both the criteria. So in such a cases, in such situations, it leads to formulate in different criterias, that is maybe of total cost should be less than or equal to the average maintenance cost per year, or should be maybe increasing than the or equilibrium in strategy. That relates to the year by year conditions, and depending upon, so we'll be recalling this depending upon these criteria, that is case number one and two, three, like that, as per this average value that changes with respect to the time towards the maintenance cost. First, in the first case, the cost of a bike is rupees 3000. The salvage value, nothing but the resale value, and the running cost are given in the table or column. And here we are having the condition that find the most economical replacement age of the truck. So we are also having the two different criteria as per the situation, that the replacement for the next year's maintenance cost is less than the previous years, hence do not be replaced at that particular situations. And if the maintenance cost is greater than the previous year's cost, hence we can prefer for the replacement. So by considering these two different steps, as per the given table or column, year wise, the running cost, that is 600, 700, 800, and a deviation of or difference of 100 to a particular extent up to the 1000, and here 200, and here 300 in the sixth year, at the time of sixth year, and at the time of seventh year, increasing or crossing of 300, and depending upon incrementing of the running cost or maintenance cost, nothing but running cost and maintenance cost, the resale value will be getting decreased simultaneously. So depending upon these criteria, we have to formulate the solution, and when it has to be replaced we have to give a justification. So considering from the tabular column, age of the replacement is first year, and total running cost we have been taken here, and depreciation cost. So depreciation is equal to the cost of the bike minus the resale value. So resale value they are already given as per our tabular column in the question itself, and it relates depreciation is equal to the cost of bike minus resale value, the difference of the value here. And finally, what is the total cost value? So total cost value in the sense nothing but addition of this total running cost plus depreciation, and that will be constituting as an leads towards the average cost per year. All right. So first one, in the first year, the total running cost is 600 rupees, and depreciation it is minus total cost of the bike minus resale value. That is here it is 1300. First one 2000 running cost resale value. So 2600. So that is related towards minus 600 relates towards this 1000. Depreciation is the 1000. Cost of the bike minus the resale value. So total cost of bike it is 3000. So 3000 minus the resale value in the first year it is 2000. So 3 minus 2 it is 1000. So running cost it is 600 and resale value it is 1000. And next one it is total cost. So what is the total cost existing? So total running cost plus this depreciation. So 600 plus 1000 leads to 600, 1600. So average cost per year it is, in the case of first year it is 1600. And coming to the point of this second one, second year. So in the second year, in the question we have been clearly specifying that for the second year we have to add the first year's session also. Second year lo వచ్చేసరికి 700 it has been charged, but already for the same vehicle in the first year also it has been charged of 600. So hence in the second year, up to the second year we have to calculate that 600 plus 700, so 1300 we have been spent. So that is the total running cost. So here total running cost for 2 years. So first year we have been 600 and second year it is 700. So 6 plus 700 that is 1300. So total cost for up to 2 years we have spent 1300 here. So hence depreciation of the bike. So what is the total value of the cost? That is 3000. So 3000 and second year resale value is 1333. So 3000 minus 1333, and here it is the value 1667. So upon the hence the total cost for until the second year, up to the second year it is 1300 plus 1667, that is 2967. So average here need to be specified. So what is the average cost? For example, we have been considered here 600 plus 713. So for 2 years depreciation or 2 years calculation. So average in the sense here, the total cost divided by how much time it has been allocated, 2 years. So 2967 divided by 2, and hence it is 1483.50. Simultaneously for the third year it is 2100. Nothing but up to 2 years total running cost is 1300, and at that particular third year, what is the total cost? Running cost. So, sorry, total cost, that is third year it is 800 rupees. So here 1300 plus 800. So that leads to the value. So 13 plus 8, that is 21. So 2100 is the total running cost up to the 3 years. And what will be the depreciation? So depreciation is nothing but cost of the bike minus resale. So for total cost it is 3000, 3000 minus here it is resale value 1000, and hence we'll be having the 2000. So this is the value of 2000. And upon addition the total cost is 2100 plus 2000, that is 4100. So average in the sense upon total cost. So total cost is the total cost for 3 years divided by how many years? 3 years. 4100 divided by 3, and hence 1366. Vice versa in the fourth one also simultaneously fourth year. So fourth year it is 2100 plus, in the fourth year it is 900. So 21 plus 4, that is 3000. And so simultaneously bike value, that is 3000 minus in the fourth year 750 resale value. So that will be the 2250. And upon addition, 3 plus 3000 plus 2250, that is 5250, divided by average, that is 4, and hence it will be coming as 1312.50. In the fifth year, in the fifth year, that is 4000, that is here, up to the fourth year, the total running cost it is 3000, and the fifth year it is total running cost, sorry, total running cost in the fifth year it is 1000, and hence here 3000 plus 1000, it is 4000, and the total cost, that is depreciation, total bike cost, that is 3000 minus in the fifth, that is resale value 500. So 3500, sorry, 3000 minus 500, that is 2500. So here it is depreciation value 2500. Upon addition, that is 4 plus 25, that is 6500. So 6500 on an average divided by of this 5 up to the time factor is 5 years, leads to 1300 value. Average cost value is 1300. So what is the major strategy here? Most economical replacement age of the truck. So what is the most economical age that need to be specified? That it should not be, we are having two different factors, that replacement is not necessary when maintenance cost is less than the total average cost. So here maintenance cost is, if it is not less than, then he can be replaced, or else the maintenance cost is very much less than the previous year, average total cost will be than the average total cost, it will not be replaced. So it is necessary when the maintenance cost is greater than the previous year's average cost, then only it has to be preferred for the replacement. And hence at the fixed point, that is total cost, it is 3000, and later on previous year it is being increasing in the strategy at the range of this total cost, that is 4000 to 5 6500. That is at a point of this fifth year, it is a compulsion that replacement of the bike is necessary, whereas this exceeds than the existing total cost, and maintenance cost is much more higher than the total or average cost that has been existing. All right. Yes, we'll be discussing regarding the second criteria in the next class. Thank you. Thank you very much.